Cool. Welcome, everybody. It turns out I have too many earrings for the mobile mic. So if I get overexcited and wander away from the microphone and you can't hear me anymore, then just wave your arms and I'll try and remember and come back here. So I'm Holly Cummins. I'm an IBMer. I've written Dr. Holly Cummins on the slides, which I don't usually bother, but I have a doctorate in quantum computation. So in this context, it is totally relevant. And in theory, I know what I'm talking about when I talk about quantum computation. In practice, actually, nobody understands and nobody knows what they're talking about when they talk about quantum, but I can pretend. So I want to start with a bit of a discussion about where we are with computers, because we work in tech, and so I think we assume that given the right team and given enough time, probably most problems could be solved. And then we look at the software we're working with, and sometimes we look at our colleagues and we think, well, in practice, actually, maybe the problems couldn't be solved, but in theory, they could be solved. But it turns out that even in theory, there are some problems that are basically impossible to solve, no matter how good a computer you have. And these can be really simple problems. So this isn't, how do I monitor my serverless cluster when I've had 20 years of development? You know, this is something simple like, I'm a logistics company, I'm an airplane company, I'd like to go to a number of destinations, and because it's 2019 and I don't want to destroy the planet, I'd like to do that with the smallest amount of fuel. Well, should be pretty easy, right? We know what the formula is for the answer. It's a well-understood problem. We've been talking about this problem since at least the 1930s. In the 1930s, we called it the traveling salesman problem, which sort of made sense in the 1930s because people were going around selling vacuum cleaners. Now it seems sort of quaint, but it's still a really relevant problem today. We still need to know, even more than we did in the 1930s, how to get around a bunch of destinations in an efficient way. No problem, right? Well, it turns out, actually, we have no idea for a given set of destinations what the most efficient route is. And it's weirder than that because we actually know perfectly well how to calculate it. We have the formula, but we don't have enough time to actually get the answer. So this is, of course, mostly true when you get a reasonably large number of destinations. So if making some assumptions about computational speed, if I was an airline company and I needed to go between 10 cities, well, I can work that out in about 25 minutes. So that's probably worth it in order to save a lot of fuel. But what if I have 16 cities? It turns out then it takes 27 years to calculate the answer. So even, I didn't even increase the number of cities by double, and yet the amount of time it took increased from minutes to years. And if I'm an airline company, I really don't want an answer back in 27 years, because by then I'll have retired. My boss will probably have retired and then died. All of the airlines that, the airplanes we're using will have been replaced by flying saucers. So the answer just doesn't matter. And this isn't unique to this particular problem. There's all sorts of problems like this where we just can't get the answer. So this is coffee, something we know and love, understand very well. Chemically, it's not that complex. There's a couple of carbon rings, a few things dangling off. You can tell I'm not a chemist. But there's way more complex molecules than that. But there's a problem once you get into those kinds of chemical systems, which is that every single part of that system interacts with every other part of that system. So if you have a really simple equation, simple system, you could represent it as a matrix, but you couldn't actually write it as a matrix like that. That's a product of two matrices. You have to write it as a 2x2 matrix. Well, there's actually the same number of things up there, so it's not that different. Once you get up to 3, well, it starts to get a little bit more, there's a lot more stuff on the right than on the left, but it's still okay. But you can see how this is going to scale. And of course, if there's one thing that we know as software engineers, the one thing that we do whenever we get a problem is we say, okay, I'm going to take this really big problem and I'm going to break it down into small problems, and that's going to make it easier. I'm going to take my huge team and I'm going to break it down into 2 pizza teams, and that's going to make my development easier. And then, of course, we try microservices, and then we realize that we broke it down, but everything was still interacting with everything else, and it wasn't actually as easy as we thought it was. And it's exactly the same here. We have this theory that says we can make things better if we can break them down, but we actually can't break it down. So it's this really computationally complex problem. We want to get that, but we just can't get there. So going back to caffeine, if I wanted to model caffeine to get, really good mathematical understanding of what it was doing, it would take 10 to the 48 bits. Now, when the 48 is sort of there in that exponential, it doesn't look like too bad a number. It doesn't look too big. But if I write it down, it's really a lot of bits. And in particular, if I thought about, I want to do a grand challenge, I want to model caffeine, and I make some really optimistic assumptions. So I say, well, I've got the whole resources of the Earth available for this, and I'm going to have the most efficient computer I could have, and I'm going to have one bit represented by one atom, and you can't really break it down much further than that. Then how many resources do I need in order to model this? Well, it turns out you need about 10% of the Earth just to represent caffeine. And this is really confusing and stupid because it's only caffeine, right? Like, it's not like I was doing something really exciting. I was just doing caffeine. So how can something that is like that be so hard that in order to model it, I need 10% of the Earth? Well, it all has to do with the exponentials. And I think even though, we're all technical, we're all numerate, the way exponentials scale still can catch you by surprise. So there's a lovely story about the invention of chess. And the idea is that the king was very impressed with the game of chess, and he said, oh, let me reward you because I'm so impressed with this. And the inventor said, okay, great. On the first day, I'd like you to give me a grain of rice. And the king thought, yeah, okay, I can afford that. And then on the second day, I want you to double that grain of rice. Fine. On the third day, double it again. Fine. And for each square on the board, double it again. So for about a week, this was working really well for the king. There was about a spoonful of rice. After that, he started to get a little bit worried. And by the end of the chessboard, he had enough rice to basically fill Mount Everest with rice. Or another way of looking at it is if you took the entirety of India, you'd cover the entirety of India with a meter-thick layer of rice, just from an exponential on a chessboard, starting with 1 grain of rice. So those numbers, they just explode really, really rapidly. And what this means in terms of our ability to do computations is that the best supercomputer in the world can simulate maybe a system with 40 or 50 electrons, so way smaller than caffeine. So what do we do? Well, of course, we don't give up. We don't declare that chemistry is something that science just can't do. We approximate. And we can do some pretty good approximations in some cases. But the interesting thing is that in some other cases, the approximations are really, really bad. So if we look, for example, at calcium monofluoride, which again is a stupidly simple molecule, if we use the best science and the best computers that we have in order to do a good simulation of it efficiently, we work out that the bond length should be around 4 angstroms. If we actually measure the bond length, it's 2 angstroms. So we're out by a factor of 2, even with our best simulation. So basically, we have no clue what this thing is doing unless we measure it. There's another example which is even simpler, just a molecule of sodium. And there we're out by, almost a third with our best simulation. So this is a bit of a problem. And it's really surprising as well, because we look at these systems and we say, well, there's a lot of computational complexity in that system, and that's why we can't simulate it. But if there's a lot of computational complexity in that system, can we actually use that computational complexity to calculate something else? And it turns out the answer is yes, which is why I'm here and you're all here. So you can't do it for all problems, but there are some categories of problems where you can take advantage of this computational complexity to have really, really cool, crazy, super fast algorithms. So then the question is, well, what kinds of problems? This is one of my favorites. So this is the problem of looking for a needle in a haystack. And that, as we all know, is hard. And this problem was first thought of not as haystacks, but as phone books. And so the idea is, if I have a phone book and I know your number, can I find your name in the phone book? Well, and the answer is, yeah, you can. You start at the beginning of the phone book and you look until you find the name. And it works, but it's really boring. And if the phone book is long, you might die before you actually find the name. And you can do things, right? So you say, well, no, I'm going to make an index of the phone book. But that's just having someone else look through the phone book before you and hoping that they don't die before they get to the phone book. So it's really, it is the same problem. So there's a similar example of that. The cool thing about that is you can actually use it not just for finding needles in haystacks or for finding names in phone books. You can use it for finding almost anything. So for example, you can use it for card games. And this is kind of a simple card game. But if I have a deck of cards, and I have one queen, and I want you to find the queen, and I turn all the cards over, well, then, the only way you can find it, unless you know something about my sneaky head and where I'm going to put the queen, is by looking through. So the computational complexity there is order of n. But it turns out, with a quantum computer, you can do it much better. So I'm going to do this demo, but you can also try it yourselves right now. So it's just on the internet. If you Google for quantum card test, which is what I'm about to do, find this. And this is cool because it's actually running on a quantum computer. It's not running on a simulation of a quantum computer. It's running on a quantum computer. So if I take my queen and I move it somewhere, so I'm going to move it over there sneakily, and then I say execute. It's going to try to find the queen using a classical algorithm, which has to look through each one in order, or a quantum algorithm. And so the classical one took 3 attempts to find the queen, which is kind of what you'd expect, right? It tries this one, and then I never quite understand what the algorithm it uses is. I think it's a sort of a super sneaky one. So then it tries that one for reasons I don't understand, and then eventually it finds that one. The classical algorithm finds it in 1 attempt. And this is the case no matter where I put the queen. So if I try again, let's put it there. If I execute, then, let's see. So again, the classical algorithm did even worse. Whatever its sneaky algorithm was not good for this. So it took 4 attempts that time. And the quantum algorithm, again, took 1 attempt. So this is sort of simple, but it's sort of cool. It's showing you that with quantum computation, you can find a hidden queen really efficiently. So if you want to get sort of down to the numbers, for 4 cards, it could always do it in 1. If I had 2,000 cards, it couldn't always do it in 1 attempt. It would be order of root n. But in general, we can search for an answer to an arbitrary problem really quickly, as long as it's efficient to verify correctness. So for that case, is it a queen was an easy way to verify correctness. But you can use it for some optimization problems and that kind of thing as well. So what's going on under the covers? How does this actually work? Well, there's a couple of quantum phenomena that go together to make a quantum computer able to do things that a classical computer can't. And the first of these is superposition. And that's just a fancy way of saying it's being 2 opposite things at the same time. Now, in general, of course, nothing can be 2 opposite things at the same time. It's a little bit upsetting. But once you go small enough, once you go down to a quantum scale, it turns out that things can be in two opposite states at the same time. This is slightly confusing and slightly upsetting. And so this is where Schrödinger's cat came from, because Schrödinger said, if I had a cat and I have something radioactive, which I know is very quantum, and I have my radioactive decay event, and it will be both decayed and not decayed. And if it decays, I smash a glass bottle. If it doesn't decay, I don't smash the glass bottle. That glass bottle is filled with poison. I have the cat in the box with the bottle. So then the cat, because the particle both decayed and did not decay, the radioactive decay, the bottle is both broken and not broken. So the cat is both alive and dead. And everything that we know about cats tells us that cats should not be simultaneously alive or dead. I should say as well that this was a thought experiment, so no cats were actually ever tortured by physicists in order to figure out whether the cat could be alive or dead. But there's another phenomena going on which makes the superposition seem really nice and understandable, and that's entanglement. And entanglement happens when you have two things that are correlated. So, for example, I might have two photons, and they're correlated, and each one is in a superposed state. So if I measure the top one, I might get one value or another. I might get true or false. If I measure the bottom one, I might get true or false. So far, so confusing. But then I add the entanglement, and I say, no matter what I get for the top one, I know that the bottom one's going to be the same. And this is true if they're quite close together, which isn't confusing. And it's true even if they're really far apart. So they did some experiments last year where they had a pair of photons, and they sent some out into space and some kept on Earth. And no matter what they would measure them, they would see that they were correlated. So if I get a random value there, I know, as soon as I've measured the first one, I know what I'll get for the second one. And again, if I measure the top one first, then I know I'm going to get something that's not random for the second one. And this is kind of weird, right? Because they're not communicating with each other, because in order to communicate, they'd have to communicate faster than light. And everything says you can't communicate faster than light. So if they're not communicating, how can one know that we measured the other one? And the answer is, well, nobody actually knows. But that's OK. So what we get at the end of that is that a physical state that is in a definite state, so it's not a random state, it is in a well-defined state, but it still behaves randomly. And two systems that are too far apart to influence each other can still behave in ways that, although individually random, are still strongly correlated. And you can see I read that out off the screen, because it's one of those things where you only have to get one word wrong, and it makes even less sense than it did before. And so quantum computing is about working out how to use these two kind of confusing principles to get computers that are kind of confusing in how fast they can go. So I can see there's some sort of quite upset faces in the audience. And really, if you find this confusing, it's not just because I'm speaking in English, and it's not just because I'm speaking too fast. It's because it's really confusing. So all of the physicists, when they discovered this, they were totally confused by it, and they spent about 60 years arguing about what it meant, because really a lot of it just seems like nonsense. So Schrödinger, for example, he of the cat torturer, he said, you must surely understand that the whole idea of quantum jumps leads to nonsense. And Einstein said, God does not play dice. So he was really upset by the fact that we got this random behavior. And Einstein was even more upset by entanglement, because of course it was Einstein that said information can't travel faster than light. And yet we had this thing where information wasn't traveling faster than light, and yet these systems were correlated. And the only way he could describe it was spooky action at a distance. And of course, nobody wants spooky action at a distance. But the good news about all of this, though, is that you can actually completely ignore it. So sometimes when I present about quantum computation, I like to talk more deeply about the physics, because I find it interesting. And then I realized that there's a cognitive bias, because I was presenting with a colleague, and he got to a slide that had a bit of physics on it, and he said, oh, I hate this bit. And I thought, how could anybody hate physics? And then I realized, oh, it's because I studied physics in university. Of course I like physics. Not everybody studied physics in university. Not everybody likes physics. But there's, in the computers that we use every day, there's actually a ton of physics under the covers. So there's, all of the electrical theory. There's a whole bunch of quite advanced science that we can be blissfully ignorant of, including me, that we don't even ever have to think about. And it's really, we're getting to that point for quantum computation as well, where it's sort of useful to know those two principles I described, but we don't need to be physicists in order to take advantage of it. And that's really cool, and it's a cool point to be looking at it, because it's in that transition from only physicists and hardcore algorithms people care about it to actually the rest of us should care about it as well. So quantum information is now becoming something that's interesting to everybody. So going back to just sort of the basics of quantum information, if we represent a classical bit as a vector, which is maybe a little bit more complex than we need to represent it as, but it's pretty simple. So if it's pointing up, it's 0. If it's pointing down, it's 1. What would that look like if it was a quantum bit? Well, it can be pointing both up and down. That's the superposition. That's the cat being alive and dead. And in order to represent that visually, we know that if we measure it, we'll have some chance of getting up and some chance of getting down. And so we represent that sort of as a probability. And so we represent it as a point on a sphere. So we always think of quantum bits as spheres rather than just two-dimensional vectors. And quantum bits kind of long to say, so we say a qubit. And what's going on there is we've got a superposition of 0 and 1. So there we have, how do I represent a superposition? Like that. Now on to entanglement. Nobody's really come up with a very good way to draw entanglement, because it doesn't make any sense. But I kind of like to draw it just as sort of a smudgy connection between those two arrows. So there's a correlation between those. And so if I know what one is doing, I kind of know what the other one's doing. So then just to reiterate, because it needs saying twice, if it's in a definite state, it can still behave randomly. And quantum computation is about working out how to use these principles. So I have haystacks again. Right. So then we go on to, well, what does a quantum computer look like? Of course, it has to have cats in it. Everything has to have cats. We say, now that the internet was invented for cats. But actually, the position of cats in science is way older than that. Way back in the 30s, cats were already, in the sort of the early theory of quantum mechanics, which then turned into quantum computing. But the interesting thing about a quantum computer is that, you've got the qubits in it, you've got the cat, but it's really, really, really cold. So the bulk of a quantum computer isn't actually the circuit, it's the fridge. So if you look at an actual computer, all of that stuff up there is basically just fridge. And at the top, it's still pretty cold, so it's about 40 Kelvin, so about minus 230 degrees, and that's the sort of the warm part of the quantum computer. And then it just gets colder and colder the further down you go. So at the bottom, it's about 0.015 Kelvin. And that's colder than the space between the stars, which I kind of like. It seems quite romantic that, you can have a lab that has something that's colder than the space between the stars. They're actually, they're surprisingly pretty as well. So we've got lots of photographs of our quantum computer, and you kind of look at it and you think, yeah, I'd photograph that too, because it's just, only a tiny part of it is the computer, but the rest of it just sort of looks quite nice. And then the actual computer bit is that. So each of those squiggles is a qubit. So IBM has a really long and interesting heritage in quantum computing. There was a famous conference where the ideas were first talked about, and IBM was one of the co-hosts of that conference, and we've been researching it since the 80s, and a lot of the sort of the interesting breakthroughs came from IBM scientists. But of course, in 2019, what we really care about is the cloud. And I think it's really nice because IBM had the first quantum computers on the cloud. And it's extra cool because, like a lot in 2019, they're freely accessible. So anybody can go to the Q experience. You have to sign up, but then once you've signed up, you can do all sorts of things. So there's QuizKit, which is an SDK for programming quantum computers. There's a big community. There's all sorts of good stuff. And ultimately, the interesting thing about it is that you can go and you can play with simulators of quantum computers, or you can play with real quantum computers. So I'm going to show a demo of Hello World on a quantum computer. So how many of you anybody used Jupyter notebooks? One or two. So the Jupyter notebooks, the Python people love them. And they're really good for data science. And they're kind of, the nice thing about them is that they mix in the comments and the output and the code all into one thing. So they're very good for communicating about data science results in particular. So I'd like to do Hello World on a quantum computer. If you actually do the math, to write down Hello World needs about 100 bits. So if I had 100 qubits, that would be really cool, but I possibly wouldn't want to do Hello World with it because I could be doing things like simulating caffeine. And the most advanced quantum computer at the moment is well below 100 qubits. So I can't do Hello World by writing out Hello World in ASCII. But we are in the age of the emoticon, and it turns out that to do an emoticon only needs about 14 bits, because an ASCII character has 7 bits. So I can do 2 ASCII characters on a 14-qubit quantum computer. And happily, IBM make a 14-qubit quantum computer available. So that's all comments. And here's some initialization code. And so the way that the Jupyter notebooks work is that you go to each square, and then you can execute it. But the interesting bit is this. And I think there's 2 things that are interesting about it. One is we have a language called Quasm as well, which is quantum assembler, which is really low level. And this is the Python library. But if you look at it, it's actually pretty low level too. So I'm programming at the level of the bits. And most of us were on frameworks on top of frameworks on top of frameworks on top of frameworks, and we can't even remember what a bit is because we're so far up the stack. And so even though this is high level in Python, the experience is still pretty low down. But it's changing fast as well. So there's another library that we have called Terra, which is all of these domain-specific libraries, so that if I'm a chemist, I don't really want to be going at the level of the register. I want to be solving problems. If I'm doing finance, I want to be solving problems. And so we've got libraries at the problem level. And the other cool thing that it will do is it will direct whether something should go to a quantum computer or a classical computer. So it will do that compilation, and it will do that direction of this should be on this type of hardware, this should be on this type of hardware. And I think that's definitely where we're going to continue to go. So if I want to write down an emoticon, I change about half of the bits, and then I'm going to run it on a simulator. And I'm going to run it about 128 times. And you can see that I get this state every single time, because all I did was just set the bits. That doesn't really tell me very much, but I can plot it as a smiley instead. And I can see I've got that. So if I go back up, and instead of having the 0 be 1, I'm going to have the 0 be actually, yes, I'm just going to comment that out. So I'm not going to flip that 0th bit. And if I run it, and then run that, Again, my histogram that's a different thing, but it's the same. And if I run it, I should get hooray. So I've got a sad face. So there are some emoticons that are only 1 or 2 bits different. So this is not very quantum yet. So if I want to make it quantum, instead of doing a bit flip on there, I'm going to do what's called a Hadamard gate. And that's making one of those cat states. It's making something that is both 0 and 1 at the same time. So if I run that, then my histogram should show me, yeah, I've got 2 states. And you can see the probabilities of the 2 aren't exactly the same because this simulator is trying to introduce, some randomness and some errors and that kind of thing. And so if I plot it, you can see I've got a superposition of happy and sad. So now we want to get even fancier. And so let's go back to just doing a bit flip there. But let's do so I'm going to do a chain, oops. I'm going to do a bit flip on bit 7 and a bit flip on bit 8. And I think that will get me, you can tell it's a live demo because I'm doing it wrong. Okay, so if I do that, then that should get me back to the happy face, and it should get me sort of a winky eye. So yeah, I've just got 1, and yeah, I've got the winky eye. So to get the winky eye, I had to change 2 bits from the goggly eye. So now I'm back to classical, but I want to make a superposition of a winky eye and a goggly eye. So I know how to do that from doing it on bit 0. And I can go back, and instead of doing the X, which is the bit flip, I can do the H, which is creating the cat state. And I know that I had to change 7 and I had to change 8, so instead I'll half change 7 and half change 8. I'll run that, and what I'm really hoping for is something that's half goggly eye and half winky eye. And so I run that, and I'm starting to feel a little bit nervous at this point, because I was hoping for 2 states, and I've got 4. And so if I plot it, yeah, I've got the winky eye, which is what I wanted, and I've got the goggly eye, which is what I wanted, but I've got that eye that sort of looks like it's licking itself, or a pirate or something, and I've got a normal happy face too. So that's a bit of a dog's breakfast, and that is not what I wanted. But it's okay, because this is where, so far we've been looking at superposition, and I sort of think, if only I could have a correlation so that when the 8th bit was 1, the 7th bit was 1, and when the 8th bit was 0, the 7th bit was 0. And that is exactly what I described when what I was trying to describe when I was describing entanglement. So I'm going to keep my flip on the 7th bit, and I'm going to do something called a CX, and that's a controlled knot. So that's basically like an if to create entanglement. And I'm going to do it between that, and I've got those backwards. So, oh, thank you. I was only doing that to see if you were paying attention. So now, if things go well, I should get only 2 states with that weird correlation, which is sort of looking promising. So even though I changed 2 bits, I only have 2 states. And if I plot it, sure enough, I've got my goggly eyes and my winky eyes, and I've got that state that I could only achieve if I had some sort of correlation. So that was all on a simulator. I can run it on the real quantum computer. There is usually a Q for them, which kind of makes sense because there's only a tiny number of these in the world, and they're freely available on the internet, so they do get used. So it's third in the queue. So I'll come back to that, and we'll see what's going on. But, oh, no. This is the video because of course live demos never work. And while we're waiting for the real one to work, last time I ran it on the quantum computer, I got something like that. So you can see there was a little bit of noise in the results. There was that 8 exclamation mark, which shouldn't have been there because it's a real quantum computer, and the systems are still being researched, and they're really hard to make. And going into the sort of the mathematics of it a bit, again, I talked about that correlation. And so I was doing it on a 14-qubit system, so the actual matrix of possible states is something like that. And I originally had those 4, and what I wanted to do was get rid of 2 of those. So I get rid of 2 of those. And again, you could never write that as a product of matrices. To get a state where there's the goggly eyes and the winky eyes, but not the other 2, you can only write that as the whole matrix. And that's why it's computationally complex. So that's about as useful as Hello World is in any other system. It shows you kind of how to work with it. It shows you that it works. But you're not going to be solving world peace with that. In general, quantum computers, there's a complexity class, if you're into complexity classes, called BQP, and that's problems that you cannot solve normally, but you can solve on a quantum computer. And there's a whole bunch of interesting problems that are in that BQP class. So for example, simulating chemical molecules, I talked about that at the beginning. That's a really obvious and natural fit for quantum computation. So if we had a 160-qubit computer, not only could we write something like, hello world, goodbye, we could model caffeine. Materials design, again, there's so many quantum interactions going on in materials design that it's a really natural fit for quantum computation. Again, because of the chemistry implication, there's a huge potential in medical research that there may be drug designs that could be done on a quantum computer. There's a really good affinity with artificial intelligence. And so if you've looked into artificial intelligence in any kind of mathematical detail, a lot of it ends up being lots of matrices and eigenvalue, eigenvalue, eigenvalue. And a lot of the quantum mechanics ends up being a lot of matrices and eigenvalue, eigenvalue. So you can see that you just need to work out how to map those problems. And there's a lot of optimization problems in artificial intelligence, and those are a really good fit for quantum computation. Lots of interesting finance implications as well. So again, you'll notice that a lot of these problems are optimization problems. And so things like arbitrage, things like portfolio optimization, good fits. Logistics, I talked at the beginning about the traveling salesman problem. There's similar problems of, well, I've got all this stuff to do, and what's the best way for me to do it? It's an optimization problem. So where next? Well, I showed you the quantum card test, and that was running on a real quantum computer, but it was small. It was only 4 cards. So, if you go to your friends and you do a card trick with 4 cards, they're not going to go, wow, that's amazing. You kind of want to do it with like 52 cards. You could do that with 52 cards if you had a quantum computer big enough. At the moment, nobody does. But the speed at which they're increasing in size is fast. So give it a couple of years, and I may be up here going, here's the 52 card version of the trick. And I think when we look at some of these quantum computers, they've got a lot of errors in them, and when you look at them physically, there was the photograph with all of the gold, but if you actually look at it in the lab, in 2016 in the lab, it looked like that, and it was just all these wires sprouting everywhere, and you kind of think, oh, well, that's not really very sophisticated compared to my iPhone or something like that. But if you look back at the dawn of computing, and if you look back at something like the ENIAC in 1946, it looked pretty much the same, right? There was, a lot of wires, and somebody needed to babysit the system full time in order to make sure it worked. So you we're at that stage in the quantum computing journey. But I think it is going to go faster because we have learned from the lessons that we saw the first time round in terms of abstraction and that kind of thing. And you know, even between 2016 and now, the systems have changed. So at the beginning of the year, we had this announcement about the IBM Q System 1. And the description I saw of it was that it was the world's first commercial quantum computer. And I thought, well, of course it's a commercial quantum computer. IBM is a commercial company. But what they actually meant by that was that it was the first one that you didn't need to run in a lab with a whole bunch of supporting equipment and that kind of thing. They had this running, I forget which one it was, but they had it running at one of the trade shows. And it was sufficiently isolated and sufficiently resilient as a system that you could actually just pick it up and run it, and you know, you could sell it, and you know, someone could have it running in their data center. It's still gorgeous. So they had an Italian design firm sort of make the, like it's all, you know, sort of it's one piece of glass around the outside and everything. And then if you take off that sort of, it's like a dustbin cover, that thing in the middle, and if you take it off, it actually looks exactly the same inside. It's still got all of those brass wires. And we like to talk about phases for where we are on the quantum computation journey. So for a long time, for much of the 20th century, you know, we were in quantum foundations. So we were learning about quantum mechanics, and then we were learning about quantum computation, but it was something that only research scientists did. Where we want to get to is this state of quantum advantage. And with quantum advantage, that's the point at which you could do something on a quantum computer that was actually impossible on a classic computer. So if you go back to the quantum card test, I was more efficient on the quantum computer because I could do it in one try. But to do it on the classical computer, all I had to do was take 4 attempts and I could do it. But if you get enough cards, there's going to be some point where the classical computer couldn't find it and the quantum computer could. Maybe not for the cards, but for, you know, there will be some problems where a quantum computer will be able to solve it. So that's the sort of the dream. And where we are now is what we call quantum ready. And so that means we can do cool things. We can play with quantum computers. You know, we can have a 20-qubit quantum computer that we can do stuff on, but it's still just sort of getting ready for when we could do something that we couldn't do on a classical computer. So then the question is, well, how many qubits do we need for that quantum advantage? How many qubits do I need to do something that I couldn't do otherwise? And, well, it depends. One thing I haven't talked about is using quantum computers to crack public key cryptography. And the reason for that is because it's a long way away. And the reason for that is because quantum computers tend to be quite noisy. Classical computers are actually noisy as well if you go down low enough. But on a classical computer, one bit will be noisy. So you have a collection of, you know, 10 or 20 qubits and you do a vote. You can do the same thing on a quantum computer. So for example, I could take 9 noisy qubits and turn them into 1 non-noisy qubit. But if I've only got 20 qubits and I take 9 to make a logical qubit that's not got the noise in it, then I've only got 2 qubits, which is just too small. So we're a ways off having enough qubits that we can do the error correction to get a universal fault-tolerant computer. And the other problem with something like Shor's algorithm is that in order, the key that you would need to factor for that to be interesting is huge, and so you need a lot of qubits for that. So we're about, you know, you need probably like 10 to the 8 qubits to do that, so we're at least 10 to 15 years away. And to be honest, nobody knows if that's possible. We think we are, but there's some really big engineering challenges still to overcome. But there's another area which is approximate quantum computation, and that's ones where getting an answer that's close is good enough. So if I'm trying to crack a key, and I've got a key that's out by 1 bit, I don't have the key. If I'm trying to do an optimization, and I've got an answer that's out by 1 bit, well, hey, I'm better off than I was before. So all of these optimization problems, the quantum chemistry, the heuristic machine learning, we reckon within 5 years we'll be at the point where we can do things on those systems that you could not do at all on a classical system. So that's cool. So really, just to wrap up, today, a quantum computation data center looks a bit like that. It's held together with duct tape to a certain extent, but I think it's probably not going to be too far between we're looking at something, like that you sort of go, ooh, wow, that's pretty amazing. And so just to finish, do go have a play. Quizkit.org you can Google, and there's lots of tutorials, lots of introductions, and it's good fun. So I don't have time for questions, which is probably as well because quantum computation is hard. But I'll be out, and I'll sort of leave this, but I'll be hanging around in the hall as well. So I'm really happy to chat sort of one-on-one if people would like to know more or have questions. Thank you all.